Welcome back to the deep dive. So today we're looking at something that feels pretty significant in the AI world.
Yeah, it's more than just another paper. We're talking about Microsoft's BitNet B1.58.
Right, this 1.58-bit model. And the claim isn't just, it's a bit better. The sources we've read suggest it's a real challenger.
A challenger specifically to GPU dominance in inference. That's the key part. Running the models, not just training them.
Exactly. So our mission today is to dig into that claim. Is this genuinely a paradigm shift? Could we actually see a CPU renaissance for AI because of this?
Or is it, another interesting tech demo that doesn't quite break through? That's what we need to figure out.
Okay, let's kick off with the numbers because honestly, they're kind of hard to ignore. Get this. Compared to similar full precision models, BitNet B1.58 uses something like 5 to 10 times less memory.
Which is already huge.
And estimates are 10 to 20 times lower energy use, plus it runs 2 to 3 times faster on a regular CPU.
You really got to pause on that energy number. I mean, up to 20 times more efficient, but, and this is the kicker, supposedly without tanking the performance.
Yeah, that's always been the trade-off, hasn't it? Shrink the model, lose the smarts.
Exactly. BitNet claims they've found a way around that.
So, okay, the central question then is how? How does a model with basically like almost no information per weight, 1.58 bits, keep up with the big models? What's the trick?
Well, it's less a trick and more a fundamental change in the math. That 1.58-bit number, it's not arbitrary. It comes from information theory.
Okay.
It's log-base 2 of 3. Roughly 1.58.
Log base 2 of 3, why 3? What's the 3 represent?
It means it's a ternary system, so normally model weights are these complex, 32-bit or 16-bit floating point numbers, expensive to compute.
Right.
With BitNet, every weight can only be one of 3 values.
Yeah.
-1, 0, or +1. That's it. 1, 1, +1.
Okay, 3 values. That sounds simpler, but why is that such a big deal computationally?
Because the single most expensive operation in any LLM is matrix multiplication. All those floating point numbers being multiplied together.
Yeah, that's what GPUs are built for, right?
Exactly. But if your weights are just -1, 0, or +1, multiplying by +1 is just addition. Multiplying by -1 is just subtraction, basically a sign flip. And multiplying by 0 means you just ignore that part of the calculation.
Ah, so you completely eliminate the expensive multiplication step.
It's essentially, yes. The whole computation shifts from being dominated by multiplication to being dominated by simple addition. Yeah, way faster, way less energy.
Okay, that makes sense. But you can't just plug that into a standard model architecture, right? You need something new.
Precisely. That's where their custom bit linear layer comes in.
Okay.
It replaces the standard matrix multiplication layer.
Got it. And you mentioned something, W1.58A8. What's that about?
Right, that's the mixed precision scheme. It's actually pretty clever.
So break it down. W1.58.
W1.58 means that the weights are the 1.58-bit ternary values we just talked about.
Mm-hmm.
Super compressed. Think of them as simple switches.
Okay, weights are ternary. What's the A8?
A8 means the activations, the numbers that flow between the layers, are kept at 8-bit integer precision.
Ah, okay, so the switches are simple, but the signals passing between them have a bit more resolution, like a scratch pad.
That's a good way to put it.
Yeah.
Keeping those activations at 8-bit, using a technique called max quantization, is critical if you tried to make everything ternary.
It would just collapse. Too much information loss.
Exactly. The numerical errors would pile up and the performance would just fall off a cliff. This W1.58A8 balance seems to be the key to maintaining quality while getting those huge efficiency gains.
Okay, clever math, smart engineering, but show me the evidence. You mentioned speed and energy, but let's see the concrete data. Is this CPU renaissance actually happening?
Well, let's look at table 1 of the paper, memory first, the non-embedding part of the model. It needs just 0.4 gigabytes of RAM.
Wait, 0.4 gigs? Seriously, that's nothing. That's less than my web browser uses right now.
Pretty much. And compare that to similar models in its class. They need anywhere from 1.4 up to nearly 5 gigabytes.
Wow, so that's up to 12 times smaller.
Yeah, and that's what suddenly makes running sophisticated AI on your phone or your laptop totally feasible, locally. No cloud needed.
Okay, that's huge for privacy and latency. What about speed on, like a normal computer?
They tested it on a standard Intel Core i7 using their BitNet.cpp framework. Latency, just 29 milliseconds per output token.
29 milliseconds, that's really quick for a CPU doing inference.
It's about 1.4x to 4.2x faster than competitors on that same hardware. And then there's the energy.
Right, the 1020x figure.
The estimate is 0.028 joules per token. That's between 6 and 23 times lower than the full precision models. Think battery life on mobile devices. Huge difference.
Okay, the efficiency numbers are staggering. No argument there. But the big question remains, is the model actually smart? Did they sacrifice quality to get these numbers?
That's the million-dollar question, isn't it? But the data suggests surprisingly little sacrifice. Its average score across a range of benchmarks is 54.19,
And how does that stack up?
very competitively. For example, a top full-precision model in its size class, Quinn 2.5, scores around 55.23. So, BitNet is right there with it. Performance is largely maintained.
Huh. But I bet it's not uniform. Are there tasks where it struggles or maybe even does better?
Yeah, there's definitely nuance. It seems the ternary structure is actually really good at certain things. Formal logic, reasoning.
Like math problems.
Exactly. It gets top scores among its peers on benchmarks like GSMAK, math word problems, Math 500, and even common sense reasoning like ARC challenge.
Interesting. So the very simple structure might actually help with structured thinking.
It seems plausible. Maybe the discreteness forces clearer pathways. On the flip side,
Where does it lag?
code generation. On the Human Eval Plus benchmark, it's noticeably behind the best full precision models. Capturing really complex high-dimensional stuff like programming syntax might be harder with only -1, 0, +1 weights.
So specialization might be the future then. Different architectures for different tasks.
Seems likely. One size probably won't fit all.
Okay, before we get to the strategic stuff, one more tech question. Lots of people have tried low-bit models before, and they often, well, they didn't perform this well. What makes BitNet different? Why did this one succeed?
Yeah, that's absolutely critical. It comes down to how it's trained. Most previous attempts use something called Post-Training Quantization, or PTQ.
Meaning you train the big, full model first.
Right. And then, after it's all trained and working, you try to brutally squash the weights down to low precision.
And that usually breaks things.
Often, yeah. Performance drops significantly because the model never learned how to function with that limited information. It's like trying to teach someone calculus and then suddenly only letting them use whole numbers.
Okay, so what does BitNet do?
They use Quantization-Aware training, or QAT.
Aware. So it knows about the compression during training.
Exactly. They simulate the effects of that 1.58-bit limitation during the training loop. The model has to learn from the very beginning how to represent knowledge effectively using only those NAMI 0 + 1 weights.
So it learns to be compressed.
Precisely. And the results back this up. BitNet trained with QAT gets that 55 average score. If you take a competitor like Quinn 2.5 and just apply 4-bit PTQ after training, its score drops down to maybe 51 or 52 on the same benchmark subset. QAT is the key to maintaining performance.
Right, that makes sense. Okay, now let's talk strategy. This is where it gets juicy. If the tech is real and the performance holds up, what does this mean for the market, specifically for NVIDIA?
Yeah, this is the potential earthquake. So remember, training AI models is CapEx, big upfront hardware cost. But running those models, inference, that's OpEx, an ongoing cost that scales with users.
And GPUs are expensive to run for inference, right? Power hungry.
Very.
Yeah.
That high recurring GPU cost is becoming a major bottleneck for making AI services profitable. So the inference market is just ripe for disruption.
And BitNet, running efficiently on cheap CPUs.
Yeah.
That's the disruptor, catalyzed by this BitNet.cpp thing.
That framework is crucial, yes. It's a highly optimized C++ library specifically for running these 1-bit models on CPUs. And suddenly, CPUs look really good for this.
Wow. What makes a CPU good at this new kind of math?
Because the math shifted to addition. Modern CPUs have incredibly powerful integer processing capabilities, especially using SIMD instructions.
SIMD. Single instruction, multiple data, the parallel processing thing.
Exactly. Things like AVX 512 on Intel chips. It can blast through tons of simple integer additions or subtractions simultaneously. The BitNet.cpp paper reports speedups of over 6 times on standard x86 CPUs just by leveraging these native capabilities.
So high-performance inference is suddenly unlocked on hardware almost everyone already has.
That's the potential.
Okay, but NVIDIA, they've faced GPU killers before. They have the massive CUD ecosystem, the developer loyalty, the moat. Why wouldn't they just squash this or, adapt?
That's the multi-billion-dollar question. The CUDA moat is real. It's software cutting-in, TensorArt, and 2 decades of mind share. Switching costs are enormous for data centers.
But aren't their current GPUs kind of bad at this specific type of math? They're built for floating point multiplication, which BitNet avoids.
Well, yeah, that's the irony. Architecturally, current GPUs aren't the ideal fit, which gives NVIDIA a choice, right?
Ignore it and risk losing the inference market to CPUs.
Or adapt. They absolutely could integrate specialized ternary tensor cores or something similar into future GPUs. They could co-opt the technology, optimize CDA for it, and try to keep everyone locked into their ecosystem. They control the software gate.
So it's not necessarily NVIDIA dies, but maybe their total dominance in inference gets challenged. We see fragmentation.
That seems like the most plausible outcome based on the sources, a bifurcated future.
What does that look like?
GPUs likely remain king for training and for huge batch inference jobs in data centers where throughput is paramount,
Hmm.
but a massive segment opens up for CPUs and eventually specialized low-bit chips, or ASICs.
Where specifically?
Edge devices, definitely. Laptops, smartphones. Also, privacy-focused applications running on-premise. Industrial AI, medical devices, anything where latency is critical or cloud connectivity isn't guaranteed. That market looks set to shift away from GPUs.
Okay, so if you're listening to this and you're an ML engineer or working in MLOps, what should you be learning right now? This changes the game.
Absolutely. You need to look beyond the standard Python libraries like PyTorch or TensorFlow, at least for the deployment side. Get comfortable with C++ inference engines.
Like BitNet.cpp or the more general Llama.cpp.
Exactly. And maybe even more importantly, start learning low-level CPU optimization.
Hmm.
Understand CMD vectorization, cache efficiency, multi-threading on CPUs. That's going to have a key skill for deploying efficient AI outside the big GPU cloud.
And if you're a founder or an entrepreneur, this feels like a huge opportunity. Where's the post-GPU gold rush?
Well, I see three main areas popping up. First, hardware. Designing new chips, hyper-specialized ASICs or FPGAs, specifically for this low-bit addition-heavy computation. A BitNet processing unit or BPU, maybe. High risk, high reward.
Okay, hardware. What else?
Second, software. The whole MLOps toolchain is built around GPUs and full precision models right now. There's a massive need for tools tailored to this new world. Think debugging tools for one-bit models, specialized fine-tuning methods like a BitLaRow, deployment platforms for CPUs.
Makes sense. The ecosystem needs to catch up. And the third area.
Applications. This is maybe the most exciting. Building the next generation of edge AI, truly private AI assistants that run entirely on your device, smarter industrial sensors, medical diagnostic tools that work offline. The possibilities explode when you don't need a data center connection.
Yeah, that on-device private AI, that feels like something people really want. Okay, finally, what about investors? Is the advice just sell NVIDIA? Probably not that simple.
No, definitely not that simple. But the investment thesis has to evolve. Focusing solely on GPU makers for AI growth, especially on the inference side, is looking riskier.
So where should the focus shift?
Short term. Look at software companies bridging the gap, helping enterprises use the CPU power they already have for AI inference. Long term, you have to consider placing bets on those fabless semiconductor startups designing the new low-bit accelerators. NVIDIA's dominance in the operational expense part of AI, the inference is no longer a given. The risk profile has changed.
Okay, so let's wrap this up. The big takeaway seems to be BitNet B1.58 shows you can get extreme AI efficiency, like really extreme, without the catastrophic performance hit we used to expect.
Yeah, and it makes sophisticated AI practical on billions of devices that aren't plugged into a giant data center. It changes the economics.
And it does this by fundamentally changing the math, right? Swapping that heavy multiplication for simple addition.
Exactly. It's a simplification at the core computational level.
Which leaves us with a final thought for you, the listener. If the main bottleneck for AI shifts away from raw floating point processing power and maybe moves towards things like specialized memory access, data flow, how you handle all these simple additions really, really fast, what kind of completely new computer architectures might we need to really unlock the full potential of this one-bit AI era? Something to think about.